Let us learn about immobilization of enzymes. An immobilized enzyme is an enzyme with restricted mobility attached to an inert insoluble material. Immobilization is defined as the imprisonment of cell or enzyme in a distinct support or matrix. This can provide increased resistance to changes in conditions such as pH or temperature. It also lets enzymes be held in place throughout the reaction, following which they are easily separated from the products and may be used again. This is an image of enzymes immobilized in beads of alginate gel. Supports or matrix used in immobilization technology. The matrix or support immobilizes the enzyme by holding it permanently or temporarily for a brief period of time. There are a wide variety of matrices or carriers or supports available for immobilization. The matrix used should be cheap and easily available. The matrices or supports for immobilization of enzymes or whole cells are grouped into three major categories. The first category is natural polymers, and the second category is synthetic polymers, and the third category is inorganic materials. Natural polymers. Alginate. A natural polymer derived from the cell wall of some algae. Calcium or magnesium alginate is the most commonly used matrix. They are inert and have good water holding capacity. Chitosan and chitin. They are structural polysaccharides occurring naturally in the cell wall of fungi and the exoskeleton of arthropods. Collagen. It is the proteinaceous support with good porosity and water holding capacity. The side chains of the amino acids in the collagen and that of enzyme can form covalent bonds to permanently hold the enzyme to the support. Carrageenan. It is a sulfated polysaccharide obtained from some red algae. Their good gelling properties, together with its high protein holding capacity, makes it good support for immobilizing enzymes. Gelatin. Gelatin is the partially hydrolyzed collagen with good water holding capacity. Synthetic polymers. They are ion exchange resins or polymers and are insoluble supports with porous surface. Their porous surface can trap and hold the enzymes or whole cells. Example: diethyl aminoethyl cellulose, polyvinyl chloride, UV activated polyethylene glycol. Inorganic materials. Zeolites. They are microporous aluminosilicate minerals with good adsorbing properties and extensively used for immobilizing enzymes and whole cells. Ceramics. They are non-metallic solids consisting of metal and non-metal atoms held in ionic and covalent bonds. The composition and bonding pattern varies with different types. Diatomaceous earth. They are siliceous sedimentary rocks formed by fossilized accumulations of the cell wall of diatoms. It is a good adsorbent and are resistant to high pH and temperature. This is the pictorial representation of immobilization methods. Methods of immobilization. Adsorption. Adsorption is the oldest and simplest method of enzyme immobilization. Nelson and Griffin used charcoal to adsorb invertase for the first time in 1916. In this method, enzyme is adsorbed to external surface of the support. The support or carrier used may be of different types such as mineral support, example aluminium oxide clay; organic support, example starch; modified sapphirose and ion exchange resins. Covalent bonding. This method involves the formation of covalent bonds between the chemical groups in enzyme and to the chemical groups on the support or carrier. It is one of the widely used methods of enzyme immobilization. Hydroxyl groups and amino groups of support or enzyme form covalent bonds more easily. Entrapment. In this method, enzymes are physically entrapped inside a porous matrix. Bonds involved in stabilizing the enzyme to the matrix may be covalent or non-covalent. The matrix used will be a water-soluble polymer. The form and nature of matrix varies with different enzymes. Pore size of matrix is adjusted to prevent the loss of enzyme. Pore size of matrix can be adjusted with the concentration of the polymer used. The greatest disadvantage of this method is that there is a possibility of leakage of low molecular weight enzymes from the matrix. Methods of entrapment. Inclusion in the gels. Enzymes trapped inside the gels. Inclusion in fibers. Enzymes supported on fibers made of matrix material. Inclusion in microcapsules. Enzymes entrapped in microcapsules formed by monomer mixtures such as polyamine and calcium alginate. Cross-linking or copolymerization. This method is also called as copolymerization. In this method of immobilization, enzymes are directly linked by covalent bonds between various groups of enzymes via polyfunctional reagents. Unlike other methods, there is no matrix or support involved in this method. Commonly used polyfunctional reagents are glutaraldehyde and diazonium salt. The greatest disadvantage or demerit of this method is that the polyfunctional reagents used for cross-linking the enzyme may denature or structurally modify the enzyme, leading to the loss of catalytic properties. This is the image of copolymerization. Encapsulation. This type of immobilization is done by enclosing the enzymes in a membrane capsule. The capsule will be made up of semi-permeable membrane like nitrocellulose or nylon. In this method, the effectiveness depends upon the stability of enzymes inside the capsule. Advantages of encapsulation. Cheap and simple method. Large quantity of enzymes can be immobilized by encapsulation. Disadvantage of encapsulation. Pore size limitation. Only small substrate molecule is able to cross the membrane. This is the image of encapsulation method of enzyme immobilization. Advantages of immobilized enzymes. Increased functional efficiency of enzyme, enhanced reproducibility of the process they are undertaking, reuse of enzymes, continuous use of enzyme, less labor input in the process, saving in capital cost and investment of the process. Applications of enzyme immobilization. Industrial protection. Industrial production of antibiotics, beverages, amino acids, etc. uses immobilized enzymes or whole cells. Biomedical applications. Immobilized enzymes are widely used in the diagnosis and treatment of many diseases. Immobilized enzymes can be used to overcome inborn metabolic disorders by the supply of immobilized enzymes. Food industry. Enzymes like pectinases and cellulases immobilized on suitable carriers are successfully used in the production of jam, jellies, and syrups from fruits and vegetables. Thank you.